All right, good afternoon. So today we are going to continue our discussion on memories. And, most of the time, like teaching in this pandemic period of time is like, well, all by myself. So that's why I played that song before the lecture. And hopefully you will let me feel like less lonely when we are having the lecture. So before we start, like there's always an important big picture that you guys need to memorize to remember is that, well, every computer that we have now is a von Neumann computer. And the big picture of the von Neumann computer is that the computer contains processor and memory. And prior to midterm, we are all focusing on the processor part. And today we are going, after the midterm, we are going to have more flavors on the memory part. But the big issue is processor and memory. The big issue with this von Neumann architecture right now is because there is a huge gap between the performance of processor and memory. So instead of directly having your processor interact with the DRAM-based memory, we need to build the memory as a hierarchy in a way that your processor not only contain the processor cores and the register, it also contains a few kilobytes or megabytes of SRAM, which is a faster memory technology. And in addition to the DRAM and the storage that we have in the original von Neumann architecture. And after we learned the first, after we start to have the SRAM cache, we know the benefit of SRAM cache, and through the calculation yesterday, you guys probably figured that out, right? So having more hierarchy is definitely helping the performance. So that's why we start building memory hierarchy in a way that in addition to just have the one level cache, we have 3 levels of cache in modern processors. So, but why this idea of making caches would work very well is because our application implicitly has strong localities. And if you think about the behavior of your application, usually you would have spatial locality on both your code and data in a way that your instruction keep moving to the next instruction if there is no branch, if you interface no branches. And and for data, we tend to like access consecutive elements in an array. So those are spatial locality. And for temporal locality, we know that we like loop. We love loops. So that's why in the code part, we still have the temporal locality because we revisit the same instruction again and again. And for data, well, a lot of the algorithms, we do reference data many times, update data many times in these applications. So we also have strong temporal locality in data. So what really means behind locality is that most of the time, even though your program is working on a large data sets, but you are just visiting a very small amount of data instructions within a given period of time. So that's why the idea of cache would work. So the basic idea of cache is like this. So we logically partition the memory space into blocks. And every time when you are looking for something, if that's not in a cache, we will load the whole cache block containing the word or say the byte or the data that you are requesting from the memory abstraction to your cache. And then the next time when you are accessing the item that's next to the previously accessed data, you will directly have the data within the cache because that stuff is already brought in the cache the last run when we cannot find that stuff in the cache. So that's the basic idea of a cache in terms of how do we capture the spatial locality. And now the issue is that, well, we know we have blocks in the cache, but how do we know this is really the block that I want? So the cache block would organize like this. So we said each block, we would store consecutive data items. So wait. Okay, each block will store consecutive data items. And for those data items, because they are consecutive, so the last few bits, or say the least significant or of their memory address will represent their position within a block. And except for that, the rest part of the address, we call them tags. So saying that, and in addition to that, we want to know if the data content that's currently in a cache is trustworthy or not. So we also need to, boy, what's wrong? Okay, so we also need, to have two additional data structure, the valid bit, which tells us if the block here is can be used or not, and as well as the dirty bit, meaning that if the data has been modified or not. So that's the basic idea of a block within a cache. So whenever you need to access a word or a byte or whatever memory address, the processor will not directly interact with your main memory. Instead, it will first go through the cache. And the cache, no, the last few bits are always standing for the block offset. And depending on how big your block is, we know how many bits we need to trim off from your address. And then we use the leading part of your memory address as the tag. And since we store the tag of the block inside the tag array of your cache, we compare that. And as we can see here, if we are looking for 0, 0, you got a hit of that. And so we just output the exact position within the block, and from the matching block, and send it to the processor. So that's the basic idea of how to access a cache. And if we cannot find a tag within the cache tag array, we know the data is just not right there. And previously mentioned, this is very inefficient. So right now, all the cache structure, we are using a hash table-like structure. So the basic idea of that is that instead of just having the separation of tag and offset in your memory address, we additionally select a few bits within your memory address to be the index of a set. So the set here means that the blocks that share the same index, or you can imagine that they are the blocks who have the same the same hash value when we are accessing them. So that's the basic idea of a set. And then so when you want to access a cache, the first thing is that you have to partition the address into 3 different fields. Offset, block offset, meaning that where in a block the data is. The set index means that which set may contain your data. And the tag is an identifier of your block. So whenever you need to access the cache, it will go through the following process. First of all, we partition the address into tag, index, and offset. And we use the offset to identify if there is a hit within a block, then which word, which byte should I output? And we use the set index to select the right set that would potentially contain your data. And then we compare the tag value with the address that you are requesting, and see if there is any one that's equivalent to the one that you're looking for. And if the case is yes, then it's a hit. Otherwise, it's going to be a miss. So this is how we access the weight associativity cache. Okay, Yizi, question?
Hi, so I'm just kind of curious about like how do we read the block offset to select the corresponding block in the data? So for example, here the block offset is 100, so it's 4. So where do we like select the 4th block?
No, it's the 4th byte within a block.
Okay. So which block?
So which block, right? Based on the set index.
Set index.
Right. So that's, as I said, you use the set index to go to this set, right?
Yeah.
And then you use the block offset, and this is the fourth, right? So 0, 1, 2, 3, 4, right?
Okay. Yeah. Cool.
Get it?
Yeah, I get it. Thank you.
Okay. All right. So I know this is difficult to understand. So today I'm going to tell you an easy way to figure out how many bits do I need for each field, how to simulate the architecture, how to simulate the behavior of cache. So in the content that I'm teaching you here, you probably won't be able to hear any other place other than my class. So, so please pay attention to this. So this is the unique formula equation that I will teach you called C equal to ABS. Not sure how many of you see this sign before, but if you have a car and you try to drive it on a very slippery road, you will probably sometimes see this light turn on. That's called anti-blocking system. So the thing is that, well, for the car safety, so we should have this ABS system in there. So that's why C equal to ABS. Okay, so that's how we come up with this equation. So the C equal to ABS, what it really means is that the C here is the cache size, the capacity of your data arrays in a cache. And A is the weight associativity, like how many blocks are there within a set. So for the previous example, like the previous structure that we see, for each set, we have 2 blocks, 1, 2. We have 2 blocks. So this is a two-way set associativity cache. So that's the definition of A. And if you have a direct map cache, meaning that each set only contains 1 block, so you should use 1 for the A. And B is the block size. And sometimes in the textbook, they use the word called cache line. So block size or cache line size, it stands for the B part. And set, S is number of sets. And sometimes you will see a word called fully associativity cache. It's a cache that doesn't have sets, or say so this kind of cache, you can consider the whole cache as has a 1 set. So the number of sets for that kind of cache should be S. So that's the meaning of C equal to ABS. And there are some corollaries here. Once you solve the ABS value, you can use the log2b to get the number of bits required in your block offset. You can use log S to get the number of bits required in your set index. And the number of bits you need in the tag would be remaining bits in your address. So that's how the C equal to ABS would work. So right now, I just want you to go through this question and have a practice of C equal to ABS real quick. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. So looks like we definitely need some discussion. So why don't you guys go ahead and open the screenshot that I sent out through the group chat, through the chat, and start the breakout room discussion. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so doesn't look like the discussion really helps. So can some of you share what your group is confused about, or what kind of question do you have, or how do you derive your answer? All by myself. Somebody else? Somebody help me? Okay, so I have Yizi. What does your group think?
We think that the offset is 6-bit, but I don't know why, because I still kind of don't understand this. And me personally,
Okay, so if you don't understand this, remember what I just said. What was the question? What was the formula?
the formula.
Yeah, I just taught the formula.
The formula. Well, can I check that again?
What was the formula? It's just 4 characters.
It's 4 character. It's C equals APS.
Yeah, C equal to ABS, right?
Yeah.
So what's the C?
C is the cache capacity.
Okay, so what's the cache capacity here?
It's 64 KB.
64 KB. right? So it's 64 KB. So it's 64 times 2 to the 10, right?
Yeah.
Bytes. How about the A?
A. A is wait, I don't remember that.
But which one has an A? Which parameter has an A inside?
Tag? I think it's tag.
That's T, right?
Yeah, T. Well,
Two-way set. Look at
associate.
yeah. So what's the A here?
It's associativity.
Yeah. So what's the A here? What
It's
number should I put?
2.
2. What's the block size?
Block size is 64.
Yeah. So that's a B, right? So S the only one that's unknown, right?
Yeah.
So we know S is 512, right?
Yeah.
So we got OC equal to ABS. So how do you get the number of offset bits?
Offset bits. I think
what's the purpose of offset?
The offset?
You just ask, right?
Maybe it's to determine like which block or which set it is in.
No, that's index.
Oh, that's index.
So what's the offset?
Offset is to determine like what block is in the set.
No. Offset is determining where in a block is the requesting word.
Yeah. Okay.
That's exactly the question you asked, right?
Yeah. So yeah, I think so now.
So in this way, how many bits do we need? Or say who determine how many bits we need in the offset?
Like the block size, because it's 64.
Block size, yeah. Right? So it's log 64, right? So what's that?
It's 6.
Okay, so your block say that, so that's why your group say it's 6, right? Yeah. And so C is not right. How about the index? Who determines the size of the index, the number of bits we need in an index?
It's S, the number of sets.
Right. So then what's the value of it?
It's 9.
It's 9. So the cache has only 512 sets, right?
Yeah.
Okay. How many bits are there in the tag?
In the tag? Yeah, this is something that I'm confused about. Like, how many in total does like an address have?
You have a total of 64-bit memory address.
Oh.
It's given in a problem. It's given in a question. So every number here is important, right? So then how many bits are there?
It's 49. It's 49.
49, right? So who is the right answer?
It's A.
It's A, right?
Wow.
So if you look at the result, right? Only 3 of you get it right. So definitely, so remember, C equal to ABS. I want to emphasize this to you because this is the most important formula for the memory hierarchy part. And surprisingly, the textbook didn't give you guys a very easy way to comprehend that. It just does the way which I just described in a lecture previously, which tried to confuse you. And surprisingly, no other professors is using this kind of easy way to let you understand. So I'm teaching you this tool, C equal to ABS. And as we just iterate, the C is the cache size. The A is the weight associativity. B is the block size. S is the number of sets. And using this, you know the offset is there for find out which word, which byte in a block are you looking for. So yesterday I saw a Piazza post. Some of you were asking about like, okay, how do I know which byte that I should look for in the memory? The answer is that just look at your offset. Here's the answer, right? And for the index, it's helping you try to figure out which set should I look for the potential blocks that contains the data that I'm requesting for. So that's related to the number of sets. And the tag is the remaining leading bits in your memory address. So that's and with this, you can solve all these parameters in the cache configuration. And given that we are not doing so well in the first run of the C equal to ABS problem, so I will give you another run. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so right now I already sent out the question and I want you guys to discuss again and verify if you are thinking correct or not. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let me see. What do you guys think? So, well, so right now I see this, and well, some of you say it's a very short time to solve, but actually if you use C equal to ABS, it's very quick. So let me, like, can some of you show me, like, how do you use C equal to ABS for this question? Okay, Debbie Song, what do you think?
For this, so the derivative C is 30
Yep.
kilobytes.
Okay, first of all, write down C equal to ABS, right? So
Yeah.
32 kilobytes.
Times 10 to the, or 2 to the 10.
2 to the 10.
And
What's the A?
A is 2 to the third.
2 to the 3, right?
Yeah.
How about B?
Since it's 64-bit byte block, it's 2 to the 6.
2 to the 6.
And then S is the unknown, which we solved for.
Right.
And
right. So what's the S now? You can see.
6.
So it's 64, right?
Yeah.
And what's the A? Well, sorry. What's the blocks? And so with log S, right? So if you do log S, what will you be able to get?
If you do,
you'll get 6, and this is what?
You'll be able to get the number of blocks, which is the number of
no, number of sets. So it's
yeah.
it's the index, right? Number
Yeah.
of sets. Sets and blocks, they are different. So each set will contain multiple blocks. And if you have an 8-way set associativity, a set will contain 8 blocks.
I see, yeah.
Okay. So what's the offset?
The offset is also 6 because
it's log 64, right?
Yeah.
So offset is also 6.
Yeah.
How about a tag?
The tag is 64 minus the index minus the offset. So yeah, which is 52.
52. So the only thing that's not correct is D, right?
Yeah.
Does it take a long time to solve?
You try.
Oh, very short time to solve. Okay, yeah, I misread your. Okay, great, right? If you use C equal to ABS, this is actually a very quick and easy question, right? So, okay, so right now, I believe most of you get it. So, well, before I show you why we need to teach you C equal to ABS, one more thing I have to tell you is that how cache interacts with your CPU. So we know we have multiple memory hierarchy. So I skip one memory hierarchy here. Like I assume we don't have L3 because most of the stuff is like iterative. So what will happen is that if you want to read data, the processor, first of all, if you want to read, the processor would do the instruction code load. So let's say I have a load word, and then the cache receives that, and cache will look up if the block containing your requesting word is indeed in a cache or not. If it's already in a cache, then and when we access the cache, we need to partition the address into tag, index, and offset. And we use the offset to locate the word within a block. We use the index to figure out if the requesting block is indeed in a cache, which set will contain that block. And we use tag to determine if the block is indeed there. And if it's indeed there, it's a hit. Otherwise, if it's not there, we would try to fetch the block from the lower level memory hierarchy into the cache that's currently missing that data. And when we try to accommodate a new block into the cache, most of the time our cache are full. So we have to kick out somebody else from the cache. So in this way, if the cache block that you selected to accommodate the new block is 30, means that the block has been modified, and the currently missing cache is the only place that has the up-to-date data of the block. We have to write it back, meaning that you have to present that update to another place first, and that behavior is called write back. So if the victim block that you selected is dirty and valid, you have to write it back first. And then you can fetch the block that you are requesting for from the lower level memory hierarchy. And if what you are looking for is in the next level of memory hierarchy, you're lucky, we can directly put the data back. If not, then it's still a miss of the next level memory hierarchy. And again, we need to find a victim block to accommodate your block, and you have to write back it first, and then fetch the desired block and return it from where the first place you can find it, and return it all the way to the cache that has the cache miss. And every time when you are handling the miss, it's in a unit of a block. We never handle the miss in a unit of word. It's always in a block. So that's what happened when you read data. And in this process, your processor never directly talk to L2 and DRAM. So that's what happened when you read data. And when you write data, it's similar. The only thing that is different is instead of just read the data, you will have, so when it's a store, and if it's a hit in L1 cache, instead of just access the data, you will set the 30-bit in your cache block, so that we know this cache block has been modified. And again, if it's a miss, we will go to the lower level memory hierarchy to fetch the block containing the word that you are accessing and put it into the L1, perform the update and set 30 and return to your instruction. So that's the whole story about cache access. So if you want to evaluate the performance of multiple memory hierarchy, including the case of hit or miss, this is an iterative process, as we just showed, right? First of all, if it's a hit, you still have to pay the base CPI. If it's a miss, you have to count what's the miss rate and the miss penalty. And according to the graph that I just showed you, the miss penalty is the time of accessing your next level cache plus the miss rate of the next level miss penalty, right? So if you keep iterating, this is how you get your average memory access time. So let me give you one example to walk through, and you will have more practice in your homework on this line of question. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so right now I would invite all of you guys to have a breakout room discussion, and I already sent out the question through the chat. Ten seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to what I learned from you guys, this is the final breakdown. So can I have some of you share your thoughts with the rest of the class? All right, I have Albert. What do you think?
I have a question.
Okay.
Less so an answer. So it's separated into 80% ALU and 20% load and store. So are the L1 cache, the I and the D, are they parallel to each other instead of sequential?
They are parallel to each other.
I see. So the ALU is for the I cache and the load and store is for the D cache, and you would have to do two separate.
No, load stores, so be careful, right? Load store itself is still an instruction.
Oh, then for load store would be IDU, and then for ALU would just be I and U?
Yes.
I see. Okay. That's
so
kind of.
So do you want to walk through that with me?
Sure.
All right. So first of all, right, if it's a regular instruction like this, right, we have to access the instruction first, right, the instruction cache first. And as I said, each address must be partitioned into tag, index, and offset to see if it's a hit or not, right? So if it's a hit, then there's no penalty because the one cycle is already incorporated in the pipeline, right? Yes. But how many cycles we need to go, but how many chances we have to go to the lower level memory hierarchy?
For iCache, in this case, for ALU is 5%.
Okay, so 5% of the chance we are going to the lower level memory hierarchy, right? And how much time do we have to take there?
To get to L2, it will be 10 cycles.
But is it always 10 cycles?
No, if 10% dirty. So 10% dirty is going to DRAM.
It's going to DRAM, right? So you have to have 10% dirty go to DRAM first, right? And this 10% happens only when you are missing, right? So 20% of the time you are going to have a miss, but 10% within that 20%, you are going to have a dirty block that you have to write it back first.
Which is 100 cycles.
Which is 100 cycle, right?
Okay.
And if it's a hit, it's also 100 cycle, right? So when you fetch the new block in, that's another 100 cycle, right?
Mm-hmm.
And then, so for this, right? And then, so for this part, right? If it's an instruction cache, every instruction need to go through this process, which 5% is a miss, right? And for miss, if it's in L1, if it's in L2, 10 cycles. If it's not in L2, 20% of the case, that would be the case. And because we have write back 10% of the case, right? So 10% of the time you are going to pay additional 100 cycle overhead, right? So that's the instruction part, right? And as you said, for data memory access, 20% of the instruction will access the data memory. And when we access the data memory, how the miss rate is about 10%, right? So what happened during this 10% miss?
You have to go to the L2 cache.
Is that good enough?
Then, sorry, what do you mean?
Okay, don't you see something here in a question associated with the data cache?
Data cache. There's a 20% chance it's dirty.
20% chance it's dirty, right? So 20% of the chance you have to write it back. And but the rest of the stuff will be the same, right? So that's how you apply this formula and you will get this answer.
I see. Thank you.
Did you get it?
Yes.
Okay, so for this kind of question, right? If you draw the flow chart like this, it's easy to solve, right? And you won't miss any detail. So for this question, the right answer is 3.37. All right, so right now, I know you guys probably have a big picture regarding how the cache is accessed. So, and why we are talking about C equal to ABS. The whole purpose is because we want to simulate the cache. So how to simulate a cache? Let's start with the most trivial, naive cache called direct map cache. So if you don't remember what is a direct map cache, here is the reminder. Direct map cache is actually a spatial cache with only one way in its set, which means that each set only contains one block. So if I have a direct map cache with 256 bytes total capacity, block size of 16 bytes, right? So you can know like through C equal to ABS, right? Through C equal to ABS, right? The S is 16, right? The A is 1, right? And the C is 256, right? And then you can get the S as 16. And by using the X is 16, using the block size is 16, you can know only 4 bits in the index and 4 bits in the block offset, and the remaining addresses would be the tag, right? So this is how you partition this address. So right now, I have this direct map cache, which contains 16 blocks, which is exactly the 16 sets. Each set has 1 block, so it has a total of 16 blocks. And you are given this address, right? So right now, I'm asking you like how many of the cache access will be a hit or miss. So I want to invite some of you to walk with me through this example? Is there any volunteer? Okay, if not, let me see. So today I feel like David is probably a good candidate. So are you around, David?
Yeah.
Do you want to walk through this example with me?
Yeah, sure.
Okay, so first of all, for this kind of question, right, we already have the C equal to ABS. And you know, when we access the cache, what do we need to do?
When we access the cache,
what's the very first thing we need to do?
Index.
Okay, so basically partition the address, right?
Yeah.
So we have to partition the address into tag, index, and offset, right?
Yeah.
And when we try to match the cache, we don't need the block offset, right? Because the block offset is only for us to figure out which word in a block that we need to output, right? So if you want to judge if it's a hit or miss, all you need is the tag, right? And the index. Okay, so right now for the first address, which set or say which block here should I look for the data?
Since index is 0, the index 0, the first.
Okay, so where is index 0?
The top row.
Okay, is there anything there?
Nothing there.
So is it a hit or miss?
It's a miss.
It's a miss, right? So now, oh boy. Okay, let me do this. Okay, so it's the miss. So now, because it's a miss, right? What the cache would do?
The cache will take the data from the next lowest memory.
Mm-hmm. Okay, and put it in here, right?
Yeah.
So when we load the data, it's the whole block, right?
The whole block, yeah.
Okay. So now, what's the new content in the block 0?
It will have the tag 10 and the data, which is 0000.
Okay, so this is it, right? We will have that the tag 10 and the data would be something, right?
Yeah.
Okay, so it contains the data because this is a 16 byte block, right? It will contain data that's with the offset from 0 to 15.
Okay. Yeah.
Okay, so now for the next address, this one, is it going to be a hit or miss?
Wait, sorry, is the rightmost column, is that the data?
No.
That's the offset.
Yeah, that's the offset.
So it will look in the same row as before since the index is the same.
Mm-hmm.
And it
so is this a hit or miss?
Wait. I think it's a miss because it's
Okay, so when you look up the cache, what do you look?
you look up first which block and then which byte.
Okay, so which block should we go?
Block 0 and byte 1000. And it'll
No, we are looking. So look at this, right? Look at this. Remember this. Okay. This is how we access the cache, right? We partition. Okay, boy. We partition the address into 3 different fields: offset, index, and tag. We use the block offset to just select the word that you are requesting for. We use the index and to judge which block that might contain your data. And we just compare the tag to see if it's a hit or miss, right?
Yeah.
Okay, so now go back to this one, right? What do you think we should do? Are we, so right now, if you look at this one, are you still thinking the second as a miss?
Well, then it must be a hit.
Right, because right now what you are having here is that in your cache, right, you are looking for index number 0. And what's in index number 0 is tag 10, right? It's a match. So it's a hit.
I see.
Right?
Yeah.
Okay. So how about the next one?
The next one that you look in the cache at index 1 and there's nothing there, so you have to retrieve the data first. Well, first.
Okay.
Yeah.
Yeah, and because it's a miss, we will retrieve the data first, right? So it's right now here. And every time when you fetch the data, it's the whole block, right? So that's why when you have this one miss, this one is also in a cache because it actually contains from 0000 to 1111 when you serve them, right? So right now for this one, you can imagine all the address between 100001 001000 to 1111 are already in a cache, right? So now I'm asking you the question, like for this one is, well, okay, I already revealed the answer. So that's why for this one it's a hit, right?
Yeah.
So right now, how about this one, the next one?
The next one is also in the same block, so it's a hit. Oh, wait, actually, okay. So you look at the index and the tag is different this time, so you don't find the data you're looking for, it's a miss.
It's a miss, right? So this time it's going to be a miss, right? How about the next one? Hello, are you still connected?
One, let me see. So you look at the first index 0, and the tag matches, so it's a hit.
It's a hit, right? So how about the next one?
This one is the same index. The offset is in the same block, and the tag.
So it's a hit, right? How about the next one?
Well, I think this one will be a miss because after the fifth one, we updated the data with the new tag, and then we to the old one.
Okay, and when this time when we have a miss, we have to replace what's currently in there with another block, right? Which is the one that you are requesting. So now the next one, hit or miss?
Hit.
Hit, right? Okay, here we go, right? So if I want to simulate a two-way cache, so David, right? First of all, C equal to ABS, we got this partition, right? And right now I partitioned this well for you first. And if I have a two-way cache, presumably each set will contain 2 blocks. Do you mind to challenging this question again?
Okay, so two-way.
The first one, yeah, the first one, hit or miss?
Miss because there's nothing in cache at all.
Okay, so then what do we do?
Retrieve data and put it in the index.
Okay, right, so put it somewhere, right? And then the next one, hit or miss?
I think it's a hit.
Okay, it's a hit. Why?
Because there's already data at that index in the cache with the same tag.
Okay, so it's already in a cache and the tag matches, right?
Okay.
How about the next one? Hit or miss?
Miss because there's no data at that index.
Okay, because there's no data in that index. So what should we do?
We'll retrieve from the next level and.
Yep. Okay. Next one, hit or miss?
Will be hit because
because the same index, we can find a block, right?
Yeah.
The next one, hit or miss?
Next one is a miss because there's we check out that index and nothing matches that tag.
Okay. So how about the next, hit or miss?
Hit because at that index we find something with the same tag.
Okay. How about the next one, hit or miss?
Hit by the same exact reason.
Okay. How about the next one?
well. Let's see. So we look at index 1, and well, uh the first block in the set matches the tag, so it's a hit.
It's a hit, right? So if you keep going, you will figure out like this two-way cache configuration actually give us a better hit rate, right? And thanks, David. And so in this way, you know how to simulate a two-way cache. So right now, I want to ask you this kind of question because this is actually more useful for you in evaluate the performance of your code. So why don't you go through this example and try to simulate the cache behavior of this AMD processor. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to what I learned from your result, I believe we definitely need some kind of discussion in groups. So why don't you open up the screenshot that I just sent out and start your discussion. Let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to what I learned from you, this is what you guys think. Can some of you share your thoughts with us? Like, why do you think that your answer is right? Well, who picked E? Who picked E? Only one of you picked E. Who picked E? I'm asking because you are the only one who gets it right. Okay, so looks like he is not, or he or she is not willing to share her thoughts. So that's my show time. So first of all, if you want to solve this kind of question, again, C equal to ABS. So you will figure out in your address, there are 6 bits belong to the offset, 9 bits belong to the index, 49 bits belong to the tag, which you already know previously. And what you need to do is that, first of all, right, you list all the addresses that will be accessed, and you partition the address into tag, index, and offset. You partition the address into the tag, index, and offset as what we previously showed in the cache simulation questions. So I write it down here, C equal to ABS. The tag is 49 bits, the offset is 6 bits, and the index is 9 bits. So first of all, the very first access first memory address that we are accessing, according to the comment here, we are going to load AI, load BI, and store CI. So the first one that I will access is actually load A0. And the address of A0, as we write it down here, is 0x20,000. And if you convert it into binary, that's actually this set of binary. And again, partition the address into tag, index, and offset. So you know the tag is 0x4 here. The index is 0 because this is the 0 set. And currently, because we just started the code, so there's nothing in the cache, so it will be a miss. And then you go to B0, again, partition the address into tag, index, and offset. The tag is 6, the index is 0, so it's still a miss. Now, let's load C0 again. Write down the address in hex, partition that into tag, index, and offset. So it's still in index 0. The tag is right now 2, and the index 0 never seen 2 before, so it's still a miss. However, because this is a two-way set associativity cache, which means that each index can only contain 2 blocks, so we have to kick out 1. And we usually use the LRU policy, the least frequently used policy, to decide which block to kick out. So then what we will kick out here is the earliest one that's entering the cache, that is 0x4. So this one is going to kick out. So right now we are accessing A1. Its address is this. Partition the address. The tag is 0x4. The index is 0. And because previously we just kicked that block out, so it's going to be a mess. And if you keep iterating, you'll find out every time we are evicting the block that we are going to access the next. So 100% of the time, 100% of the time, you will not be able to find your stuff in the cache if your processor is like this. If your processor is like this, and if you write code like this. So now, given you know how to simulate a cache, let's try if Intel's technology would give us better performance. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to what I learned from you, looks like we definitely need group discussion again. So go ahead, do it. Let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, wow, the answer did change a lot. So can I have some of you sharing your thoughts with us? Okay, even though you get it right, you still don't want to share? Okay, so here's the process, right? First of all, again, we need to partition the address into tag, index, and offset. And that's exactly the same code, so the address will be the same. The only difference is the tag cache architecture. And because for this cache, the offset in index is plus together is going to be 12 bits, so it's 3 digits in a hexadecimal. So you can easily partition the address and separate 20 as the tag. And the index will be 0. And the first access is always a miss, same here. And what's different here is that right now for index 0, because this is an 8-way cache, so you can accommodate 3 blocks here. So so when you serve this miss, you don't have to kick out any blocks. So in this way, they are all hits here. So, and only when you are entering a new index, then you will have misses. So, and this new indexes happens once every 16 elements of A array, B array, and C array. So that's why the overall cache miss rate would be 6.25%, meaning that about like 93.75% of the time, the Intel cache is a hit in compared with the AMD processor, that's always a miss. So that's how you see why sometimes, well, the clock rate doesn't determine anything, or sometimes why this code is running on one processor but not on the other. It's all because the processor core is not the only thing that you have to consider when you are running the program. So before you leave the classroom, I do encourage you guys to review the slides today, because I don't think we are doing a very excellent job for the cache part. And this is the most difficult part in the computer architecture, I agree. But this is also the biggest part that we will test you for the final. So make sure that you understand that. And reading quiz due this Thursday. So there's nothing for you to do tomorrow. So I would suggest you go look up your assignment 4 and see by how much you would understand what the assignment 4 is asking, and by how much you can apply the techniques that you learned today in assignment 4. Other than that, enjoy the rest of your day.